This is about interpreting OCaml GADTs in Cog, and my co-author is Takafumi Saikawa. And so starting point, well, giving a bit of context, well, this is part of the Coggen project. And well, what's the original problem is that proving the correctness of the full OCaml type inference is hard. I tried, and well, we can prove it theoretically for subparts, but well, combining all of that is rather complex. And well, another option, we could write a type checker for the type syntax tree of OCaml once you've already type checked. This might help, but it still suffers the same difficulties that you need to define a type checker for the whole, another type checker over the whole of OCaml. This has never been done, is it? Entirety, I think. So what about an alternative approach that is ensure that the generated type syntax trees enjoy type soundness by translating them into another type system? Here we'll be using Cog for its expressiveness. So what's the idea of soundness by translation? Is basically your is a pointer. Yeah. So you translate your program from OCaml to Cog, translate input, reduce. If in Cog you can also reduce it. You want a way to translate that and force reductions. And so if your translation is injective on types, and if reduction commutes between the two, it means that basically subject reduction for Cog should imply soundness on the OCaml side for individual programs. So we can have this kind of argument. Of course, for this to commute, you would have to prove that actually the reduction is the same on both sides, which is another story. But let's give it a try. And what is the current situation of Coggen? So we have a backend that already translates many features of the language. So we have core ML with algebraic data types, reference, exceptions. We have even while, for loops, lazy values. So it's already a reasonable part of the core language, at least. And the natural next step, of course, is to add GADTs. But they present specific challenges. One is generation of equations between types, usage of these equations for coercion, and in OCaml you can also prune unreachable branches. So you need to reproduce all that on the Cog side. So in this presentation, well, what I'm explaining here is that we have Coggen is automatically generating all that as backend to OCaml. But in this presentation, we study how to do it, and what we will see is only untranslated example. We are not yet at the stage that we do that automatically. Okay, so what kind of GADTs we can consider? Let's go for very classical examples that I think we've already seen somewhere at CFP this year. So vectors, you have 0, successor, at the type level, and then nil. So you have vectors with fixed length. So nil has length 0, and const has length suc of n. Okay. And I think so. We can in OCaml we can define a map, which isn't going to change the length, and we can also define head, which taking a vector of length n plus 1 is going to return its head, and doesn't even have to consider the case of the empty list, since this cannot happen. Okay, so we want to translate that to Cog. What happens? Well, let's go first for the naive translation. So we are just going to translate GADTs to Cog inductive types, and we are going to rely on Cog's pattern matching construct for equation handling. And this kind of works, if you look at that. So, well, the translation is really one-for-one. It's a direct one. And now we consider, I can define the map function. What change? I think I have really here to write a few annotations on the pattern matching to ensure that it's correctly able to see that the n inside coincides with the n it gets inside. There's a technical problem in Cog for that. And otherwise, it is able to do actually most of the type inference automatically. So we only need to annotate the match construct. Okay, so no problem. But what about the head function? And this here that things are really falling apart because, well, I can try to define a direct translation of the head function, but I've been careful in Cog to add a file before, because I know that it will fail, and it fails. It tells me non-exhaustive pattern matching, no close form for nil. So it has been completely unable to determine that nil cannot happen. Why is it so? Why is it so? Actually, the deep reason is that there is no way to prove that 0 is different from suck inside type. So as types, you have no way to prove that 0 are different from suck in Cog. There is a very good reason for that. Actually, this is in the PhD thesis of Theo Winterhalter. There is a model of Cog using just cardinals of the types. And if you see that here, they would have both the same cardinals, so there's clearly no way to distinguish them. Okay. Is there a way to fix it in Cog? Of course, we can write these kind of things in Cog, so what's wrong here? The point is this: if in Cog, actually, rather than using type for the both parameters, so I go back to show you, I did a direct translation. And the point is that both the contents and the lengths were defined as types. Okay, so if rather than using types, I use nat, I put them as values, then Cog is able, of course, to distinguish them. And it's actually, it will be able to accept this definition, correctly seeing that nil cannot happen. So, so what's the situation? What's happening here? What's happening here is that actually GADTs are inductive types are not the same thing. They look very similar. I think there is clearly an influence of inductive types on GADTs, but they are not the same thing, because in GADTs, indices are simultaneously types and first-order terms. So you can use them as types, but they're really first-order terms because pattern matching results in unification. So it's a first-order unification. And the unification is going to generate equations in case of success, and it is going to allow you to prune enrichable branches in case of failure. You're really completely relying on unification, and for unification, you need first-order terms. What's happening with inductive? Well, indices and inductives are either types or values of a type. They cannot be both. I mean, so what happens as a result is that pattern matching results, well, in something that superficially looks like unification, but is not quite. You have kind of substitution if the in-pattern syntax was used. It's able to substitute in the types. And it's also able to prune some reducible branch by discriminating on the head constructor only, and if the index belongs to an inductive type. So it should not be a type itself. Okay. And so an answer, well, in the previous example, of course, I could have solved the problem by going in somehow the Haskell style. Well, let's say that actually my index is not in type, but it's in a specific inductive type. Here not would have been sufficient. Well, but that's not really true, because I can certainly come up with example with GADTs that are used as both simultaneously, because GADTs are both. So I need a translation where they are both. And since they can be both at once, it means that my translation will need to have a representation that is both as type and as term. So I call it an intensional representation, intensional translation. So in order to iterate and still keep it, we give both syntactical and semantical representation to OCaml types. So the syntactical one here is, well, utterly trivial. I have to collect all the types in my program, okay, in a big type. So it's a whole program compilation, something people have been doing for ML'22. Okay, and this is the syntax I use. You might not be used for Cog, but actually it's closer to ML, so I suppose that everybody can read it. It's a reflex syntax. Well, when I translate then the definition themselves, I'm going to do some things a bit different from the previous version. I will insist first on the second point, is that when I translate indices of GADTs, normal type parameters are still going to be, of course, in type, but indices are going to be in ML type, because then I can really handle equations of them. And the other thing is that I keep the equations explicit, because then I don't need a convoy pattern when I want to use the equation. But it's a rather technical reason. It would be perfectly correct to still do it the original way. Okay, and then I need to connect the two versions. So I have a function that translates from ML type to type, an interpretation function. And of course, since I'm going to use it all over the place in my programs that I want to evaluate, these functions should be computable. Simple definition. So int are 63-bit integers. There are 63-bit integers in Coq. We can keep the semantics. Bool, row, okay. So in most cases, we just call Coq type recursively on the arguments. And we translate ML0 and ML_suc, whereas actually we will not really use 0 and suc in the translation of the programs. And for vec, well, the first parameters is just a type parameter, so it's translated. And the second one we keep as an ML type, so no need to translate. Okay. Then what happens with this translation of terms? Well, for the translation becomes just a bit more verbose. So you need to put a lot of Coq type around. But otherwise, it's very similar to what we had before. Okay, and apparently in this case, I don't even need to use the equation that I've put in the type, because they're created by the match construct itself. Okay, and of course, all the point of doing that is that this time I can define head. Because what happens here is, of course, that since, okay, my T1 and T2 are ML type, so I have, what I'm saying here is that in L, the comparators will be an ML_suc of T2, and then in the nil case, I have an equation H, which says, if I go back, it says that in this case, N should be ML0, so since ML0 cannot be ML_suc, this properly eliminate this case. So this is not that construct, the equation is a bit deeper, so I need to extract the equation and match again on the equation, but that's no deeper than that. Pretty easy. Okay. This is not all I get. So I get the able to prune branches. I also get the injectivity on the equations. I can prove injectivity. For instance, suppose that classical. So I define equation witnesses here. And I can take you that suc is injective. It means that if I have an equation that says suc of n1 is equal to suc of n2, then it means that n1 is equal to n2. In the naive translation, I cannot get that exactly from the same reason as before. In this version, I can. So this translation here is a bit heavy because I put the equation, I wrap it. So, but otherwise, it's well, if you're used to code, maybe you can read this kind of code. Basically, I'm just going to extract. I extract the equations. So I get this W here, which is the equality witness. WEQ is going to extract the equation, and then I'm using this ML_suc to get the parameter of suc. That's just it. And this way I have injected. So nothing, no big deal here. So is everything rosy with this interpretation? Okay. Somebody here knows that it's not. Well, what happens actually? This was a comment by a reviewer, and I had just discovered the problem a bit before I got the comment. Actually, that what happens if we have existential type variables? Up to now, actually, there was a story. We have some kind of an heterogeneous translation. So for the type parameters, if it's a normal parameter, put it in type. If it's an index, put it in ML type. If it's both, if it's a pi parameter, you can duplicate it. And Coq type is going to take care that they are synchronized. But if it's not a type parameter, if it's an existence type variable inside the type definition, then you have no way to duplicate it. And you need to put the correlation between the two. So we end up with this situation that actually, well, what's happened, H list is the type for heterogeneous lists. And okay, so if you look here, quote A is used as a type of values, and quote B is no place for H list, so it's an index. So actually we have an index which is split here. We have an index here which is split into a type for values and another index. So we need from an index to create a type for values. So this is really a case where you need both views on the same type variable. Okay. And well, what happened in that case? When I translate it, actually, I need H list to be aware of Cog type. So I first define H list and then Cog type, but there's a material reflection between the two, between an inductive and the function, something you cannot do in Cog. And this is not even well founded, actually. So this is not so nice. But by bypassing the guard, the check, I can still do this definition. So in Cog now you can bypass almost anything. So, so this works. Morally, the risk of I think so actually. So Kenji Maya suggested me some ways that we could avoid this, and I think I have almost a solution involving moving this to a relation rather than a function. So I have Cog type. We will have first a relation, then a function that generates the relation. This is getting a bit heavy, but this could at least give us a proof that doing so actually is still correct. I hope. Okay, so that's actually the end of my story. I'm just giving a way to do things, so I've put a bit of corrected words because, of course, I'm not the first to do translations from OCaml to Cog. There is Cog of OCaml already. This is already 8 years ago and still in development, active development. But I know that they have problems with the ADTs. There is also HS to Cog. I know that they have problems with the ADTs. Okay. And I gave a few other papers that are, I think, kind of related to the Coggen project. Okay. And oh, I should finish. And what do I need now to get the full type-sound transpiler from OCaml to Cog? Well, for the full language, it's huge. But first, you need, for GADTs, we need to obtain a trace of how the compiler generated equations. We need also a trace of how it is good using them, because in the case of OCaml, none of this is available. So we need to do something inside the type checker to get the information. Well, Coggen itself supports already many features. As a result, in particular, I translated in this talk, I translated ML' to Cog type T1 to Cog type T2. In the case of Coggen, there is a monad in between that requires some slapping. And well, there are many open problems. So. And this is the end of my story.
Thank you very much.